Hi everyone, in this video I'm gonna explain how to solve this problem. The problem asks us to show the function defines a measure. So first notice we're dealing with a bunch of non-negative measurable functions and we have a measure space. We have a measure mu and some sigma algebra. So we essentially we have a collection of measurable sets. And now let's recall the definition of a measure. So for a function to be a measure, it has to satisfy those two axioms I'm gonna write. So the first one is the measure of empty set would be 0. And the second one is if we have some disjoint EJ, disjoint measurable EJ, then the measure of the union of those EJs would be the summation of mu EJ. Yeah, this first one makes sense, right? Because the measure is essentially we assigned a size to a set. So if there's nothing in the set, then the size of the set would be just 0. And the second one is, I think we could understand it by thinking of some probabilities. So if we have two independent events, and such as A and B, PA. So A, B are two independent events. Yeah, independent events. Then it makes sense, right? PA plus PB would be the probability of those events happen. Both of the events happen. So that's the two axioms we're gonna show. Now I do want to emphasize how we're gonna do the problem is by using indicator functions. So remember, if we're integrate some function over a set, then all we care about is how the, like, for example, we have some function and we know maybe the integral of the function is the area. It's the function and between the function and the axis. Then if we're only integrate the function over some specific set, say this is our A, then eventually what we care is those area. So we don't care the area outside of the set. So it makes sense for us to use the indicator functions to kind of simplify the proof. So let's do the first one, the empty set. So if we have an empty set, and then the measure of, or the integral of f over empty set would be just the integral of f times the indicator of the empty set. So the indicator of empty set would be 0 constantly. So we have 0 d mu, which is 0. Now let's do the disjoint unions. So suppose we have some EJs, which are disjoint and measurable, also countable. Then the measure of, that's called the union of those EJs, to be E. Then the measure of mu over the set E is just the measure of f. It's just the integral of f times the indicator of the the whole set E with respect to d mu. And since we have some disjoint union, the indicator of those set would be just the summation of indicator of each set. So then we have f times summation of ei d mu. So which is essentially summation of f times each ej or d mu. And then notice we're dealing with the non-negative functions, so we can interchange the summation and integration. Then we have the desired result.